Doing great today. Okay. Hydride affinity number for the secondary carbocation is 247, whereas it's 231 for this one. And remember, hydride affinity tells you how much the carbocation wants to react with hydride, so the lower the number, the more stable the carbocation is. These are both secondary carbocations, but you've got a free energy difference of about 16 kilocalories per mole. And to try to put that into context, if you compare the stability of a primary carbocation versus a resonance stabilized carbocation, let's see, the numbers are 266, and for the resonance stabilized one, 256. So on average, resonance can get you 10-ish kilocalories per mole. This structure is stabilized by more than you'd expect for resonance. And if it were a localized carbocation, you'd expect these two to be similar, right? Yeah, go ahead.
How do the number of carbon atoms factor into these comparisons? Because you were saying that makes a difference.
You're right. How does the number of carbon atoms factor into these differences? It certainly accounts for some, like perhaps some of that is why this one's a little bit lower. I think my instinct says, I don't know that this is true, though I'm sure there are data that would tell us one way or another. The farther away you get from the carbocation, the less it matters. So you're right, this isn't a perfect model compound, but it may be good enough. Yeah. All right, so you could draw similar resonance structures for the molecule, let's see, whoops, the less substituted molecule on the bottom. And in this case, I won't draw them all. We can fill in the rest of them later. But we would conclude that the resonance structures are probably major contributors to the actual structure of this molecule, and it probably is a non-classical carbocation. And what's the difference? Well, it's just that methyl group, so you'd be tempted to say that sterics were somehow involved. It's possible that it's easier to distort the ring to make this kind of bond, to get this carbon close enough to these two, than it is if you have a methyl group there. Your text doesn't really offer an explanation, it just says that it's context dependent, so yay. You should be able to anticipate the possibility of a non-classical carbocation. Given an experimental result, you should be able to rationalize it with a non-classical carbocation, but you can't predict, well, I wouldn't expect you to be able to predict whether one should be, I wouldn't have expected you to predict this effect with the methyl group versus without the methyl group. And in part, this is why the subject is controversial, because minor structural changes have big consequences, and so different people would publish, hey, this looks like one, and then these guys would say, no, actually, we have a related molecule and it isn't, and so on. One example where this will show up is in terpene chemistry. So you may have seen before the molecule that looks like this. This has two isoprene units. One of them is here and the other is here. And this can close up to form a bicyclic ring system, which is always somewhat fun to draw. I'm not sure I remember which enantiomer forms, so I'm just gonna guess. Oops, that's not the right one. This is called alpha pinene, and sorry, not yet, it isn't. You have a pi bond attack a carbocation that's 1, 2, 3, 4 atoms away. You do sort of Markovnikov addition of the carbocation of the carbocation to the pi bond, and you make the new bond between 1 and 4 so that the more substituted carbon can have the positive charge, and then you do an E1 style elimination to give you this alpha pinene structure. Which, if you wanted to draw, you could do something like this.
And like, what do those red and yellow lines represent?
Isoprene units. So these terpenes are derivatives. Well, this molecule is called isoprene. It's got 4 carbons and a branching methyl group. Isoprenes are synthesized from precursors in biology of the following structures. We talked a little bit about them when we talked about the squalene synthesis last time. So when you see a natural product like this and it's got branching methyl groups, you can often identify 2 different 5-carbon subunits. So in the process, it turns out that this intermediate doesn't have to go to alpha pinene. In fact, there are other molecules that can form. So I'm going to show you one of them. Hold on. Yep. So from this same precursor, let me move these background molecules out of the way. You can get the following product. So I'm going to draw that product and we'll look at what's different and we'll see if we can think of sensible ways to get from here to there. So we could draw this as follows. Okay. So one question we can ask is, how on earth do I get from here to here? Because nature takes the same starting material. This is called the terpenyl cation. Takes that same starting material and generates multiple molecules from it. I mean, just as an aside, a big component of the smell of citrus is this molecule, which is called limonene. And these terpenes are found in all kinds of essential oils, which I won't comment on essential oils, other than to say don't spend a lot of money on them.
Dr. Price?
Yes?
The alpha pinene, is it the same as the chair conformation?
Yes, those two are the same. You could draw this in multiple ways. I'm trying to think what would be the most helpful way to draw it.
Okay. And the triangle thing is facing down because of the dash?
Because of the dashes here, yep.
Okay.
Let's see, I'm going to try to draw this maybe in a way that'll maybe be a little, I don't know, helpful or not. All right, so you can view this in a couple of different ways. But look at the differences between the two, okay? Both of them have the same number of carbons. You can identify branching methyl groups on one of those carbons, so probably this one is the same, right? And I can identify another branching methyl group here. Probably those two carbons are the same. So how do I get from one to the other? If you look at the bicyclic ring system of alpha pinene, you have a ring on this side which has 1, 2, 3, 4, 5, and 6 atoms. And then on the other side, you have a ring that has 1, 2, 3, 4 atoms. Okay? That's a bicyclic, and we won't worry about naming bicyclic ring systems. But then if you come down to this other natural product called camphene, you've got on the left-hand side 1, 2, 3, 4, 5, and on the right-hand side you have 1, 2, 3, 4, and 5. Okay, so we've shifted something over. All right, so let's have a look at this carbocation here, and let's see if we can find some way we could rearrange that carbocation that would give us something that could lead to camphene. All right, so let's just say, all right, can you think of a way, well, maybe it's actually just better to look at it this way. Can you think of something we might do here that would change the ring system from being in orange 1, 2, 3, 4 to being 1, 2, 3, 4, 5? I saw, were you using the force to start something there?
I'm pretty sure you can move the bond between the 2, 3 and just slide it over.
Okay, that would be a carbocation rearrangement, right? A 1,2 alkyl shift. Literally what that would look like if we tried to draw this cation in sort of a shape that resembles its actual conformation. Here's a positive charge here. Here's the alkyl group, and we're literally going to have that alkyl group lean over into that empty p orbital and make a new bond there, and that's going to leave a positive charge on what we originally called carbon 3. 1, 2, 3, and 4. All right, so we're moving this group over. That's a 1,2 carbocation shift. Any questions about that? So let's look at the carbocation that forms if we do that, and this might give us a sense for why that carbocation shift might be favorable. Okay, and if I can redraw this molecule like this, 2 methyl groups here, oops, and a positive charge there. Okay, when you see a bicyclic ring system like this with a positive charge adjacent to the bridgehead carbon, I want you to be thinking the possibility of non-classical carbocation. So let's draw what those resonance structures would be. The three atoms of interest for our non-classical carbocation are these three. And we can name them 1, 2, and 3. We can draw a resonance structure. Where we move the bond between 1 and 2, and we make a new bond between 1 and 3. So in that case, this bond would be gone. Here's the new bond we made, and the positive charge would be on carbon 2. Salud. All right. We could also draw a resonance structure where we made a pi bond here and a positive charge there. 1, 2, and 3. Such that we'd have sort of a, overall, if we wanted to draw a hybrid structure, it would look sort of like this, where, oops, that methyl group doesn't go anywhere. We'd erase this bond, and we would have a dotted line there, and another dotted line there, and a dotted line here for a pi bond and a positive charge just shared between all of those. Okay. Do you see anything here that is anything we've done in terms of the carbocation rearrangement followed by resonance stabilization, or followed by the resonance structures we drew for this non-classical carbocation? Do you see anything there that might be similar to camphene? One interesting feature of camphene is that you have 2 carbons in one of these 5-membered rings that has the 2 branching methyl groups, and then this group on the same sort of 2-carbon chain. So when we move this bond between 1 and 2 over to be between 1 and 3, let's look at the 2 rings in the, let's look at the 2 different rings in this bicyclic system that we have. Let's start with this one, 1, 2, 3, 4, and 5. And then we similarly would have 1, 2, 3, 4, and 5. Wait, no?
No.
I went wrong, right? Oh, right, hold on. Sorry. Yeah, sorry. Our perspective changes. The bridgehead carbons used to be these 2. Now they are these 2. So we can number 1, 2, 3, 4, 5, and then we could number 1, 2, 3, 4, and 5. Okay? So we could redraw this, if we wanted to, we could redraw this carbocation as looking like this. Still a bicyclic ring system with 2 5-membered rings fused to each other.
The
Which-
line by the black one, it means it's a pi bond, like a double bond.
Where?
Or
What black line? Sorry.
Oh, like red and black line.
Here?
Like bonds, like red and black bonds together, it means pi bond.
Right here? I'm sorry, it's still,
The resonance structure.
in the resonance structure, yes, this would indicate a pi bond. All right, so this can be difficult to see. I'm gonna write the purple and orange numbers on it again to try to help make it a little clearer. 1, 2, 3, 4, and 5 versus 1, 2, 3, 4, and 5.
So how does it switch? Because we have the two bridging ones. Like I see how it's that in the first example, and then we switch to the second one. I'm just like starting to see how it flips or changes.
So the idea is that once you get here, you're gonna get to this structure through this particular resonance structure, but these are all the same. What, can you point out where
Yeah,
you're seeing
just
something
like
flip?
Where we flip the numbers from the second resonance structure down to like the one that you drew just
Okay.
now.
So I'm literally, I'm taking this molecule, grabbing it on either side, and tipping it over about 90 degrees.
Oh, okay.
Yeah. Three-dimensional reasoning on a paper is pretty tough, and this is about as hard as it gets. Then, do you see how we get to camphene from this new intermediate?
Do you just do the beta hydride again?
Yep, just do the E1 style elimination, and that gets you to this product. Okay, so terpene chemistry is tricky because we had to do a 1,2 alkyl shift. Then we had to recognize this as a non-classical carbocation or as closely related intermediates and see that we could move this bond between 1 and 2 to become a new bond between 1 and 3. Effectively, what we're saying is you could look at this in a couple of ways, right? You could say, well, it's actually a 1,2 carbocation rearrangement to make the new bond between 1 and 3. Alternatively, you can say, and in that case, that would be a step in the reaction. In contrast, others might say, actually, those are two resonance structures of the same thing. So it's subtle, and you don't actually need to take a side. You could draw the mechanism either way, and it would be fine. Yeah?
So do we see any other double bonds forming, like any other different kinds of rings based off these resonance structures?
Would you see any other kinds of rings and double bonds forming because of these resonance structures? Let's see. You wouldn't be surprised to find a resonance structure, to find a product with the following type of structure. I don't actually know. Oops. I'm just looking on all the pictures I can find on Google for terpenes, and I'm not necessarily seeing that. Oh, there's one. Yeah, is that an option? It looks like a reasonable option. I'm not seeing a particular natural product that looks like that, but that doesn't mean it doesn't exist. All right. Cool. And I'm not sure if you'll encounter mechanism problems like this in the future, probably from me, but now I've told you how to deal with them. But in other classes, particularly if you take natural products, I think this kind of thing would show up. All right, that was kind of an aside, and I think we're pretty well done with carbocations now. what we want to do next is talk about conformations of organic molecules. This is a subject near and dear to my heart because I love peptide and protein chemistry, and conformation has a lot of applications there. I am going to restrain myself, though, and not talk about peptides and proteins today or tomorrow or on Friday.
Can I ask a question?
Yes.
I don't understand. Like, what is that bond? Like, is it like the same like that bond, or what is that?
Okay, so in these resonance structures, this red bond here. I'm sorry. The red bond there, I didn't mean to indicate it was a pi bond. I drew red over the original bond that was there just to indicate that that was a bond we were going to change in going from one resonance structure to another. All right. Did that answer your question?
Yeah.
Okay. All right, so we want to talk about conformations, and this is just a quick review of some old boring stuff that you already know. You guys are familiar with eclipsed versus staggered, yeah? You're familiar with the idea of a dihedral angle. Have you heard that term before? Yeah? Okay, dihedral angle is technically the angle between two vectors or between two planes. It's just math. If you have the coordinates of each of these points, you can calculate that. But it's easiest to think about the dihedral angle as being, if you look down a carbon-carbon or whatever bond, sigma bond, or whatever kind of bond in a Newman projection, and then calculate the angle between any two bonds projecting off the front carbon, one on the front and one in the back, that's a dihedral angle. So, for example, this dihedral angle between red hydrogen in the front and blue hydrogen in the back is 60 degrees. On the other hand, red hydrogen in the front to green hydrogen in the back, that's 180 degrees, and so on, okay? And then if you make it more complicated, let's see, by the way, where does this energy barrier come from? Why is eclipsed less stable than staggered? Okay, Gauche interactions we're going to use to describe why there's why two different staggered conformations are different. But you're thinking right. What is it that makes this a problem? Go ahead.
I mean, hydrogen, the nucleus is a positive charge, they're trying to repel each other.
Okay, so you've got electron-electron repulsion probably as these line up. Remember, you can think of this a couple of different ways. One is just electron density, though, and sort of it's, you may have been taught it as sort of a Sterics argument. I sort of have a hard time accepting the Sterics argument because if you just go ahead and draw ethane and then look at it and then even see it maybe in space filling, I don't really think that the hydrogens would be that close, or rather close enough to bump into each other, right? So there's a couple other explanations. One of them is that you have a bonding orbital here and another bonding orbital there. They're lining up. You'd have closed shell repulsion, basically two filled orbitals interacting. One goes lower, one goes higher by a larger amount, and so you have repulsion there. There's another argument about hyperconjugation where the anti-bonding sigma star from this carbon-hydrogen bond overlaps with the filled sigma orbital from this carbon-hydrogen bond in the back. Those are two different explanations you'll encounter. Then you've seen this kind of plot for butane. You've seen that there are a couple of different staggered conformations, one with methyl overlapping with hydrogen and the other with methyl overlapping with methyl. Because of Sterics, the methyl-methyl overlap is worse. Then there's different staggered conformations. One we call gauche. That's when the methyls are adjacent to each other. That dihedral angle is like 60 degrees. And then here is an anti-conformation. This is where the dihedral angle is 180 degrees. There's another gauche conformation as well, though they haven't drawn it for you, but you can envision it. It's simply where the methyl group is on the other side. If we were able to somehow restrict rotation around this carbon-carbon bond in butane, these two gauche conformations would be enantiomers of each other. Do you see how they're mirror images? So we actually have a way of talking about that. If the methyl group is, if the methyl group, or sorry, you've got the group in the front, and then if the group in the back is on the left-hand side, we call that plus. So this would be the gauche plus conformation. And that's just a positive dihedral angle. And then if the methyl group in the back is on the left, we'd call that gauche minus. And I might be getting that exactly wrong, and that's okay. I'm not going to ask you to assign which one is plus versus minus, just that there are two that are the same, just have opposite dihedral angle signs. All right. So no, I don't think I want to talk about that or that. I guess that's simple enough. As you start adding more carbons, interesting things can happen that are difficult to predict unless you're able to think about the whole chain. So I'm going to draw a pentane, and we'll look at it. Notice that in pentane there are multiple bonds to think about in terms of rotation. All right. Let's number the carbons from the left, 1, 2, 3, 4, and 5. Notice that there's not really any conformation to worry about in the bond between, or there's not any conformational equilibrium to worry about in the bond between 1 and 2, because either way, it's just all hydrogens on that first carbon. Right? No matter how you rotate the thing in the back, the conformations are equal. In contrast, if you look down the bond between 2 and 3, we've now got a couple of possibilities, right? As shown here, the methyl group in the front is anti to the other group in the back, but it could be gauche, right? Similarly, if we look down the bond between 3 and 4, the methyl group in the back is anti to the group in the front. And again, that's anti, but it could be gauche. So we have to consider not only the all anti conformation, which is the lowest energy one, but then there's the next higher one is the gauche interaction, where the bond between 2 and 3 is gauche, but the bond between 3 and 4 is anti. We might call that, people talk about conformations with abbreviations, G for gauche and T for anti, because trans, I guess, I don't know. People can't get their act straight. So this would be a GT conformation, gauche between 1 and 2 and T between 3 and 4. You could also call it TG and it would be the same. You would pick whether it was G plus or G minus based on the which side the methyl group was on. If we rotated it around to here, that would still be gauche conformation, but the other-handedness. Okay, we can have another possibility. If you look at this possibility, you see that the bond between 2 and 3 is gauche, and we'll say that the group in the back is on the right-hand side of the group in the front, so we'll call that gauche minus. Similarly, looking down the bond between 3 and 4, the groups are gauche, and the group in the back is again on the right-hand or clockwise side of the group in the front. So that's also gauche minus. So these are 2 gauche conformations where the handedness or the sign of the dihedral angle is the same. Naturally, that's worse than having 1 gauche and 1 trans or anti-conformation. But look at this massive difference. It's almost 10 kilocalories per mole between the gauche minus conformation, where the twist around both bonds has the same handedness, versus this one. Okay, just looking at it, down the bond between 1 and 2, the group in the back is on the left-hand side of the group in the front. So we'll call that gauche plus, but if you look down the bond between 2 and 3, between 3 and 4, the group in the back is on the right-hand side instead of the left-hand side. So this is a gauche plus, gauche minus conformation. And the reason this is so bad is it puts those methyl groups on the ends really close to each other. We can look at that in a space-filling sense, and you can see that they're actually bumping into each other quite a bit. And if you want to go back and look at some of those angles, you can see that actually some of them are not that close to gauche. If you measured this dihedral angle between this group in the front and this one in the back, that's somewhat larger than 60 degrees. And the reason it is if you make it a perfect 60 degrees, those methyl groups bump into each other. So sometimes people call this, I want to get this wrong, I'll probably get it wrong anyway. Sometimes people call this a syn-pentane interaction, and in particular, well, I don't think I have any more to say about that. I was going to say, you can take the same number of carbons, and if you attach this carbon to that carbon and get rid of those hydrogens, suddenly that steric problem goes away. Because now they're not bumping into each other, they're actually bonded to each other. All right, next time we need to talk about whether gauche interactions are always bad, and we're going to see the impact of heteroatom substitution on conformations about carbon-carbon bonds. All right, so I'm posting the exam today, and you can have till Monday.
We should submit it on Monday.
Yeah.